depth of the algebra for these orbital trajectories and the energy and momentum and all of that. Now I'd like to show a more elegant way to visualize the geometry of the orbits that we talked about. And we'll start off with a very direct application of the geometry to Rutherford scattering. We've already talked about this arrangement for a pair of hyperbolas of major radius A, minor radius B, but there's no necessity in hyperbola for having one bigger than the other. They can switch places very easily. But the idea is to get this thing connected to an actual scattering. So that's the first thing we'll talk about. And this will give us a chance to see some more of the envelope geometry that we worked on with the oscillator orbits, many trajectories, and then a contacting envelope. We have some really pretty simulations of that as well, and this one is no exception. Then this thing called the eccentricity vector. This is a symmetry object, and it's very much analogous to the Stokes vector, describing the two-dimensional coupled oscillator or polarization states. But this works for the orbits and is a little bit trickier, but also very beautiful. And then, in having written papers about this and used it in classes, I discovered a parameter system that is much closer to the geometrical part of the orbit theory, and so we'll talk about that as well today. The connection formulas between these two is a little bit tricky, but it helps when you are dealing with orbits in an abstract way, but also for real cases of space flight and astrophysics. I think the most interesting Coulomb orbits are the ones that exist at the center of our galaxy, and apparently all other galaxies too, that involve objects orbiting at enormous speeds because they're orbiting a black hole. And this stuff works pretty well for it. It's in a relativistic system, but there's some things here that make it go a long way and be able to handle some very high speeds. So we have some more animations that we'll see today, and some other things that are connected to this, plus American Journal of Physics papers that are, of interest if you want to go further than what we'll be talking about today. So let's consider the Rutherford scattering thing carefully here. I'll get them on 3 screens at least. We'll have actually 4 screens to start with. But anyway, the actual construction that I want to demonstrate is on the 3rd screen there. And it starts just by assuming that we have a beam of, well, in this case, alpha particles, alpha plus 2, and it's the gold 79 nucleus that was being targeted by Rutherford, these experiments. And what you imagine to start with is a beam in which you have, say, equally spaced impact parameters. That's what the dashed lines are supposed to represent. And there's this particular a trajectory that we're going to calculate, just a ruler and compass derivation, has at a great distance, a certain distance to above, lying above the line that goes dead center. So the gold nucleus is sitting here at this focal point. This is an empty focus. There's nothing there, but mathematical significance of this is just as important as that one. So the main focus has a gold nucleus sitting, and then alphas are coming in horizontally and experiencing the Coulomb field of this object and deviating away from it. Now the construction that we won't spend any time on this time, but it's something that is quite equivalent, and that is if the alpha particle were a negative charge and was attracted to the nucleus, the conjugate trajectory right here that bends around it feels its attraction and continues out. A scattering that occurs for it is in many ways identical to the one that we'll get for the repulsive case. So that's another topic that we'll bring up in the last few lectures of the class. So anyway, remember the formula that I told you never to forget for Coulomb energy. The K over 2A. That marvelous energy, total energy, that is only a function of the parameter A, not the B. Only the major axis is important. This is true whether it's repulsive or attractive, whether it's hyperbolas or ellipses or circles or parabolas. So in this case, the dead-on closest approach is what we're imagining here. We're imagining that lucky alpha particle that gets the biggest push by bringing it to a complete stop. And then it just turns around and skedaddles out of there at the same rate that it came in. So once you know that that happened, then you know right away that 2A is the distance that it got to. And that's what this formula is telling you. So all of these things have a certain energy E. No matter what that energy is, and whatever the constant, it depends on the charges and all of that. But we're imagining that it gets a certain distance away, and that distance is twice what we call the semi-major parameter, axis parameter. Okay? So then it's just a question of taking this picture and realizing that for all the other orbits, to be in the same circle, we're just going to lift it up or push it down by a certain amount. And that's what the construction in the third screen there is doing. So see if there's anything else I need to mention here. Well, one of the things I want to mention is that Rutherford never really got the alpha particles to impinge on the actual nuclear structure. Well, and some people would say he didn't even come close, but he still got to within very small distance, and that much smaller than anyone I could think. Now, I also should mention that these alpha particles in these pictures that we're drawing here are already inside the electron shells for the gold atom, well inside there, up in Springdale and down in South Fayetteville, compared to this picture that we have here. So there's a long distance where the alpha particle basically is traveling through just a very weak electronic wave function. And electrons are 2,000 times lighter than a single nucleon, and this is an alpha with 4, so we're not even considering that at all, and that did not register on any of the experiments that Rutherford did. So it's a clean problem. It's a very clean piece of physics that's going on here. So let's get this on all screens here so we can talk about it. The basic idea is that if you want to find out what's going to happen to the alpha particle that's on impact parameter B equal a unit, or any of the higher ones, well, it's just a matter of drawing a circle at the radius A away from the vertical. And then the next step is to just copy the angle between the line, draw this line, and then copy that angle to there. And bingo, you found this direction this thing is going to scatter out on. It's that simple. Is that more or less clear? So this tipped over alpha pattern that we're looking at is tipped over for this particular scattering by exactly that amount. Okay? So this is one of the kinds of angles that, this is the forward scattering. How much forward are you in your scattering? And I would call this the backward scattering angle there. So at this point, if that's all you want is scattering angle, well, that's how you get it for a particular impact parameter. So the next step is to find the focus, the other focus, the one that has nothing sitting around it, and get all of these up to that point. Here, all I have to do is, after I've drawn this line right here, put a compass there and strike an arc over to this line. So we know the two foci are balanced around the center of the orbit. And then the next step is, which we'll draw pictures of that I used to make everybody in the class go ahead and construct from these two foci the actual hyperbolic points, say a dozen of them, and that's what we'll show pictures of in just a minute here. So that's basically it. And the backward scattering angle right here divided by 2 that's this angle right here, is this angle, has this as its right triangle. So that is what we're dealing with here. Now, half angle is complementary. Full angle, supplementary, or whatever you call it, 180-degree difference, high difference. Okay, so using these two focal points and imagining a string going to the actual point that the orbit is, that's the more tedious part of any of these constructions that we'll be talking about today. But just getting the basic geometry first really is helpful. So let's look at it a slightly bigger picture here, and go with the actual construction. And there's the beginning of it right there. But the basic idea, as I say, is either the back scattering or the forward scattering, whichever you want, but this one is easier to envision for low impact parameter, and the other one is easier to visualize for high impact parameter. And see if there's anything. The other thing is that there is a focus locus to this hocus pocus. This line right here is where all the foci will be parallel and 2A far away from the beam face, the line perpendicular to the beam direction, just above the actual gold nucleus, which is there. So all of the foci are on that line for all of the different impact parameters, either scattering up or scattering down. So that is kind of neat, and that's what we're looking for in all of the more complicated constructions that we're going to be doing. So the actual procedure for calculating the orbit is just take the compass and strike an arc. Anything bigger than 2A is fair game, and just happen to pick that one right there. And then be aware that the distance r prime to an actual orbit point for a hyperbola that we're talking about here, the difference between r, the distance to the prime focus, or the original focus, and then the empty focus, the second focus. Okay, this is r, and this is r prime. The difference between those two lengths is just 2a. That's this distance right here. So you figure out where this thing hits, and then you simply subtract the r prime from that, and you measure that distance, r minus r prime, take that, whatever that distance is, let's see if I've got this right here. Actually what you do is you use the r that you picked, and then you find out what r prime is, and you take the compass and set it to that, and put it on this focus, and strike an r. You get 2 points for the hyperbola. Then you just do it again with a slightly bigger r, get a slightly bigger r prime by a subtraction down there, and strike that arc off, and then do it again, and you know, pretty soon you have a pretty good idea. This is just a half a dozen or so points, and then the same number up there. A pretty good look at what the alpha particle is actually doing, and it's pretty amazing that it is already this high above its original beam direction that it would have had if the nucleus wasn't there. It's already that high, and then bingo, it's going to be going up, and some symmetry around this axis makes this reflection of that. So there's a typical orbit constructed, just ruler and compass. We take it. No algebra to speak of, except for that k over 2a energy. That pretty well settles this. I should have been following along here. Just look at it again. That's the drawing, and then that's the trigonometry that goes with it, which we're going to be using to get the cross-section, the differential scattering cross-section for this. So, okay, now that's pretty easy. There's the right triangle, gives those two scattering angles. Take your pick. And well, that's that formula is what we really need in order to get that. Now let's let the computer do the job. That's why you're not sitting here now like in the old days. I taught this course working a ruler and compass on some graph paper. I will ask you to do one such construction for the next problems, and it's a good way to remember how this works. But anyway, this is this comes out of a program I wrote quite a long time ago called Cool It, and TC has really made it a much better. This is the old crummy program right here, but now we can make much nicer orbits, and all of these orbits have a beautiful envelope. Okay, that is little, very analogous to the envelopes that we made with the volcanoes of Io, or in the very small atomic laboratory, the cesium atoms that make a little fountain that we use for and that the National Institute of Standards uses to keep our time. The difference, of course, is that the parabola that was the outside of the fountain, this has got empty space where that was. This is now sort of the flip of that. This is the alpha repelling all of these orbits, making this perfect. Well, it turns out it's a parabola. We'll see that we can prove that fairly easily. So, what I'd like to do probably is turn on this one, and I'll probably do it best on this computer. This is a little faster than this one, even though it's older. And I'll take this one down to that point as well, so you can see what it is we should be getting if this works. So let's go ahead here now. Several points in this lecture, there are pages that show the control panel for Cool It, where we do a lot more than just this particular scattering event. And also, before I go on, let me emphasize that when we're thinking of the alpha thing, that's something happening in a tiny little space. Here's something that's happening as we ride on our little Earth around the sun. and both of us travel around the galaxy, around the Milky Way. And what's amazing is that this is an approximate model, and it's a pretty good approximation for deep space H-atom scattering from the solar wind. So there are a bunch of hydrogen atoms. Everyone knows this is the case because 20-centimeter spectroscopy tells us that the universe is filled with hydrogen. It's not very dense, but you take enormous volumes and it begins to make an observable phenomena. And for each spectral part of the hydrogen, Lyman alpha is this particular one that I'm thinking of, because that was what my friend Darrell Judge discovered as the Mariner Mars Mariner not satellite, but space exploring, like one of the first to make it into the vicinity of Mars, crossed the bow wave of our sun, the Lima alpha bow wave. There are a lot of others, but this one is really pronounced. And it's about 1.2 astronomical units from the sun being right there. So we're sitting on Earth right here, we're sitting in a spacecraft, and it crosses this thing. That's amazing. And not only that, but it pretty much has this shape. That's something that hasn't been measured very far, but basically been measured in this area, but we've seen it on other situations. So we know it's something that's a pretty good approximation. Now you remember, the solar wind consists not just of light, but of quite a number of particles that make a more substantial wind. But we are just talking about light here, the photons at the frequencies that involve Lyman alpha, UV radiation. And the electric field vector, the radiation goes inversely with distance, but the intensity, the thing that really counts, goes as inverse squared. So there's a repulsive Coulomb force coming from the sun, and this is experiencing it, making the envelope. Okay, so that's another application of this thing in the large as compared to the alpha scattering business. Anyway, enough talk. Let's run this scattering here and see if it can get it started here. I should have tested this darn thing before. I'm always having trouble with this guy right here. That seems to be the right website. Let me go back, see if I can pick this thing up. Okay.
Kill Firefox and start afresh. You have no idea what state that's in.
Oh boy, I didn't have any trouble with this when I tried it this morning.
Yeah, I tried it too. We double triple checked, but
Yeah,
not here at the wireless.
that's,
Signalless is what they should call it.
yeah, something weird's going on here.
If you quit the app altogether.
Force quit.
Yeah, it just
Firefox.
might be hung. See, it's hung. Not
Yeah.
responding. So the next launch ought to get it. You've got bars.
Okay. And I'm set to pick up Firefox when I do it again, but let's see what happens. Go here. 2. This thing's covering it, so I can't see what I'm getting. Let's go back and see if I can pick it up by starting it.
I was installing an update.
Oh,
I think that host us a week ago too.
Here we go. So here comes the, and we're assuming, we're just looking at the set of alpha particles that's started here. They're still pretty much in line with where they would have been at basically many angstroms away. But you can see only about now as they start to bend a little bit, and the one that's dead on is still moving toward the gold nucleus, if we're thinking of that experiment Rutherford, and now it's stopped. and now it starts to go back. But the others are doing other things. And there it is. That's the formation. And then there's sort of a little contact region right there that are contacting this thing. There's a parabola. And that's the movie, okay? And of course, if you want to resume, it's set to stop at a particular place, you can let it go and make the whole parabola, and they all go off the screen. There's the thing. Now, what's going on also here in this, we're now imagining the quantum mechanical situation I am. TC has made the program so that you can plot the action, just picking up, particular units, but the colors here represent the actual quantum wave that would be associated with the wave function for this whole scattering event. And the only thing that's missing, of course, is the amplitude of that wave. The frequency wave number is given by the colors, but this ridge here could have an evanescent lip, that is an exponential lip, a little bit off the side. Aside from that, that is the basic wave function structure gotten with classical mechanics, and we talked about this back at the end of Unit 1, Chapter 12. So that's this picture right here. Now, one of the things that you notice, you strike a compass, and from here it doesn't fit very well at this point. Bring it over a little bit. There's pretty close to a circle center. This circle, you can see it works very well for that point, but then it starts to get outside of these points here, and then get inside of them here. So obviously this isn't part of a very good circle, but it gets better and better as you get closer and closer to here. And then this is the interesting thing that we'll talk about next chapter, sort of, is that this center creeps, just keeps creeping closer and closer. For this particular scattering event, those alpha eventually are on a circle going away from this point, even though they've had to go through this elaborate dance to get to that state. So, there's a lot to be seen by, this is just stuff that you don't find in mechanics books. They should be in there, now that we have computers to make us see that, but that's the way it goes. Anyway, the number that this is 221 of the suckers. Obviously, with a faster computer, you can use more and just smear the thing, but this is certainly enough to see what it is we're getting. Okay, now the analysis of the geometry for this is, since we've talked about the kites of a parabola, the kite plays a role here. And this came long after I'd written the paper on that, and we still haven't published anything about this little structure that I'm going to show you here. But remember that the second focus is on this focus locus right here, second focus locus. Okay, and at this particular juncture, we've picked an impact parameter that's right here, and we just draw a line through there till it's above the center, and that's where you make the next asymptote. This is the forward scattering angle right there. Then there's the asymptote that this trajectory, the green trajectory, is going to be approaching, having left this asymptote. So the incoming asymptote has the stuff that we showed. It slowly rises above the thing. There's the closest approach to the nucleus, okay, and then it's going to come back as we go way out there. Finally, we'll lay back down again on this asymptote line. But what we're interested in is where it makes contact with the envelope. Now, I've drawn the envelope in here, but how do you find that envelope? You see, and that's the curious thing about this, is that what you do is you go up here and you look at this particular point here, and you see where the center of that is, and you make, and I'm more interested in how that line right there intersects at that particular point. I draw a kite turned up. This is the front top of the kite right there. The yellow is the bottom of the kite. And remember the kite, the parabolic kite that finds a tangent on a parabola. There's the center of the kite making the tangent, and this little point here indicates exactly what the slope of that tangent is. Well, the same thing's happening here, except it's sort of cattywampus with respect to the that picture. And once you've found this thing where it intersects, and then have a certain point associated with a line from here to there, that's just double this, and you then can construct the line that's the center of the kite, and that will be the tangent that's hitting this particular envelope. There's the contact point. And remember that contact point is being played off of this focus here, as well as the second focus. This is a parabola though, so its focus is at infinity. The envelope parabola's focus is, there's only one of them, the other one's gone. But then this is the other focus right here, it has to be in line with that one at infinity. And so you then finish this construction in just by having that particular point there. So you can see the parabola right there just seems that thing, and then the envelope continues and curves over to make the other points, turning points, you might say, of the caustic, I guess that's the name for the envelope that's maybe appropriate here. Okay, so that's, I think, neat way to look at the gears behind all those orbits and making of that envelope there. This is just a better picture of it, a sketch. The actual construction on graph paper is here, where you can see this is a B equals 3 hyperbola contacting a little bit lower on the envelope. So the red thing is the envelope, and then this is the actual, that particular alpha particle that was contacting there, then continues out here and eventually gets to the asymptote, up a few yards to the left and up. Okay, so at this point you check to see if your geometry is working out, and we get about 2-figure accuracy, maybe one figure to be ungenerous, but that's the actual scattering angle that is coming for this particular orbit right here that has 3 units of impact parameter. Okay. All right. Now remember the kites there was a square kite, and then there was the sort of the Asian kite that was very symmetric. That's when you go inside the focus of the parabola. Well, I got an example of first the square kite right here. This occurs right here when you have the B equal to 2A. If your impact parameter is equal to the major diameter of the hyperbola, that's when you get a square kite, and the contact point sitting right there. The weird case is when you go inside focus, make the impact parameter less than that, really heavy scattering, then you get an Asian kite. In this particular case, there's the contact point right there. Okay, so this kind of makes it possible to visualize things that I don't think have been seen before. Okay, let's see if anything else I have to say. The scattering geometry, but we're interested in, or if you're Rutherford, you're interested in how much of the stuff you're getting at a particular angle. You're interested in differential scattering cross section, and that is basically mapping this little input window right here, differential of the impact parameter, some small distance, and everything that goes through this window here has to come out in this thing right here. Now that, of course, is not pointed at the origin. Remember, these the points that these loci move in, and this is another one that starts out here someplace and eventually moves into this point. So your actual scattering will intersect with this one. This one is going to close in on that, and that angle right there, the differential scattering angle, will eventually meet. But in the meantime, all we're going to do is count. Everything comes in here has to come out there, so we're going to figure out what happens as something that comes in from x equal minus infinity and then goes out to r equal infinity. We're talking about an area that is just the polar metric, sine theta, d theta, d phi, and phi we can pretty well drop out fairly quickly here. So this is the incremental solid angle into which that will scatter. And the ratio of these two, d sigma to d omega, that's a derivative. It's an actual derivative of b with respect to theta, which is what comes up here. This has to have symmetry in order to work. So the azimuthal angle, this angle around the beam, is dropping out. So it's this thing, and by geometry, this b over a is cotangent. Turn that derivative, the db d theta, is then cosecant squared. So we have to put that in. That's, of course, inverse sine squared. And that has to be equal to, this is the formula to never forget, k over 2e is the a, that is, the energy is k over 2a, so the a is k over 2e, and putting all of that together gives us a formula which is very simple. It's the fourth power, inverse fourth power of the scattering angle is the amount of stuff coming out per solid angle after scattering at infinity. That's what you're seeing in that tube right there. So all this stuff cancels to that, and that's kind of neat. Now what's neat about this also is that this classical result agrees with the quantum mechanical one that's usually used in describing Rutherford-Kelvin. And it's called the first-born approximation. So it isn't the most accurate thing that you could possibly have. There's second and third and fourth approximations give very small changes to scattering the energies we're talking about here. But this is an interesting case where classical mechanics gives a quantum mechanical result quite closely. Okay, just for the fun of it, I want to make a contrast between the total scattering cross-section of this thing. This thing that has a sine to the fourth here, you know right away you're in trouble with this. This is going to blow up. Okay, trying to figure out how much of the beam actually got eaten by this Coulomb field, and it's all of it, basically. That's the conclusion that arrives from this. Now, if you do something like this, and I will go ahead here, get this thing back into the slide mode, and go ahead and run the animation for this particular case, just to make the point that differential scattering cross-section has a total cross-section for some things. Most simply is this one right here, which we call hard sphere scattering. So here come those alphas, and now there's some kind of weird potential there. It's absolutely hard, bounces them off, and off they go in a circle. It's not quite centered, but when you get very far away, it'll look like it is. But the total cross-section for this is exactly that, the area subtended by that sphere. And that's something that's interesting to do. If you want to try these formulas out for this, it turns out to be pi r, where r is the radius of the ball. So that's what you get for the total cross-section. And that's what you should get. It's just eating that much of the beam. But that's the thing about the Coulomb. Infinite. This just keeps working, right? And it's the best way to see that I can think of. Okay? All right. Let's see if there's anything else. I think we're ready to do the general case. This is very nice for something that starts at infinity. The alpha beams start very far away from the scattering center, and that's what made that geometry really simple. But the next thing is simple too, but I would say much more powerful in the sense that we are doing a general case. All possible Coulomb orbits are being tackled now. We're going to get a geometrical construction that works for everything that's Coulombic. Okay, and it involves this weird vector called the Lynch vector usually, but it's got more names than that. It's actually the Laplace-Hamilton-Gibbs-Runge-Lynch vector, and maybe some more. I mean, after a while, your name gets down to here. Maybe I'd stick mine on for the little tiny contributions that I've given to the geometry of this thing. Okay, but this guy's always got his name in practically everything. That guy's pretty smart too. Here's the American that helped or independently discovered this. So what I'm doing for the sake of comparison, remember these two potentials, the 1 over r and the r squared, those have this higher symmetry that allows us to play games with vectors that describe conserved vectors. Besides angular momentum, these are all isotropic potentials, but these are isotropic in some kind of higher dimension. What higher dimension? Well, some of this will be discussed in the group theory class that I hope to give in the spring. But this one is actually an orthogonal group in 4 dimensions. This is a generalized 4-dimensional sphere, which is an outer product to 3-dimensional spheres in a weird kind of a beautiful way. And then this one is very obviously the unitary group of, well, 2, if we're talking about a spin half, but this can be generalized as well. So this is just for the sake of comparison of what this thing, this magical vector with 5 names is going to be giving us. And it's not the way it's stated. It's usually stated without the constant there. They put it on this thing, and they call it A. But what it is it's the eccentricity. So it should be called the eccentricity vector. You won't, if you look up eccentricity vector, you won't get this. But if you look this up, you'll see it, and it won't be stated quite that way. But this is the way it makes sense geometrically. If you want to do ruler and compass constructions, this is your baby. Okay, so that's what we need to describe here. And here's the proof of it. Here's what shows that given what we did the other day, which was build an orbit equation out of R, this thing gives you that equation by simply considering the dot product of it with the radius vector. So there's epsilon dot r. Now I found it amusing to also consider the dot product with momentum. So remember what we're doing here is working with a vector that is conserved. We know L is conserved, angular momentum, that's conserved by any isotropic potential. But this very special O4 potential is conserving this crazy thing. So, dot it with R, dot it with P, you'll get something that, if you're lucky, makes some sense. Okay. Now, I'm going to skip over most of the things that we do with this, but it will be part of the story. This is the one that you should probably look at, and that's the one we're going to construct mostly today. Now what I want to do is let there be an angle between wherever this vector is and the actual radial vector. This thing's standing still, the r is on its orbit, whatever elliptical or hyperbolic orbit it makes, it's going to be having a variable epsilon dot r. But I can write it as cosine, that's the dot product, and then while I'm at it, I can switch the dot and the cross here, so I get r cross p dot L. R cross P is L, so this is L dot L, that's L squared, that's a constant. So this particular term right here is a constant. This is the thing that's going to be variable, and so is this variable because it's got an R on it. P moves as well. This is the thing we have to finish. That will be our pièce de résistance today. Anyway, there are the components of our hopefully intelligent geometry. And you can see right away from looking at that center screen, that's how it matches. Just writing the dot product of epsilon with r and letting it be adjusted, the algebra adjusted a little bit, I can get you r equal L squared over km divided by 1 minus epsilon cosine. Sound familiar? That's the equation of a general conic. Remember the one that we used as the epsilon, okay? So that's why I call this the epsilon vector. It is the epsilon that is the eccentricity in the general conic. Jackpot. So, just to check it out, okay, for phi equals 0, you're talking about an apogee. That's the thing that's off the screen there, the high point, apogee. And then pi over 2, right here. That's our lattice radius, no longer called lattice rectum. Forget about that. And then with a larger number, 1 plus epsilon, and you got a smaller number, that's the perihelion distance there, and perigee being the low point in the orbit. Okay, if it's an elliptical orbit. But the thing is that this is going to apply to all of the conic orbits, attractive or repulsive, all of them. It's taking care of the whole schmeal. And that's what's so really powerful about it as far as classical geometry goes. If you're talking about an attractive, and remember when k is greater than 0 by our convention, that's attractive because we write the potential as minus k over r. And then when we make it repulsive, which I'll put right here, let's get these things all on the screen now. There are the three cases that our orbits can be, okay? Only one of them is elliptic, but it's a pretty large case, and we're living on an elliptic orbit of the Earth around the Sun, and then the Sun and Earth around the galaxy, and so forth. The energy here is less than 0. And then the other attractive orbit is when you crank that energy above 0, you get a hyperbolic orbit. And then, forget those two, let's take a repulsive Coulomb, the Rutherford case, where we're scattering things that repel each other. The energy there are always greater than 0. We don't have an energy less than 0 case for this repulsive Coulombic field. Now let's go back to the graph here and connect with the eccentricity formula right here. Here I've got the momentum going this way. I've got the angular momentum right-hand rule. The L vector is out of the screen. Say, if you want that to be your origin, which would make sense, that's where the scattering would be about. And this then would be P cross L with a minus sign there to give us this vector. And you see, that's the idea. Epsilon plus that vector, would give me the radial vector. Okay, so there's the radius, there's the P cross L, and there's the epsilon vector. The eccentricity is represented by a vector that measures how eccentric the orbit is. And it's a circle that shrinks to 0. And back to doing sophomore physics. But all of the rest of the cases, including this one, this is quite neat. If I crank the energy up, then this attractive orbit is attracted by that force, but it's got so much speed that it's get straightened out. And in fact, if you make it really fast, it's just a straight line. It doesn't even have a visible bend in it. But nevertheless, it will still be treated by this same sum formula right here. So there's the minus P cross L, and the sum of that and that gives you your radius vector at all times. And then there's this weird guy, okay, the Rutherford case, okay, repelling. In this case, this is a nothing burger. The second focus is nothing there. The actual attractive, I should say repulsive, force field center is right there. And then this is an attractive force center, and this is too. This is the nothing burger sitting inside the orbit, and there's the nothing burger focus sitting outside. Okay, so those are all the cases, and that's what we needed to before we're done with the lecture here today. Okay. All right. Just to remind you what we had to go through in the last lecture, and the results are being stated here. The table of physics versus geometry is pretty much the same as the one I gave you. I added this little piece there just to help. So what I wanted to do now is talk a little bit about the geometry that has to do with the P dot R, but I'm not going to do much with that. It is a kind of a neat thing. It says the projection PR of the momentum onto the radius. It's the R or R prime radii. Either the radius that actually comes from the force center or the radius that comes from the nothing burger focus. That has to be epsilon times the projection px onto the x-axis, the axis that has the eccentricity vector, the unit eccentricity vector. Okay, so that's kind of a neat thing that we can use for some stuff. It's kind of hidden in what we're about to do. This particular graph is not taking into account the fact that the P is going to get big as we go to the thing. That will become obvious later on. That's the, it falls, it gets faster as it falls towards the center. At this point, that thing makes the most sense, but what we're really at here is realizing that these two radii, this now big R prime radius and this now right on the lattice radius line, these two always, no matter where they are bisected by a line. In other words, equal angles here and here. This bisector of the dual radii has to be normal to the tangent vectors, that is the momentum at every point. Now, what's going on here? This is something we kind of skipped when we were talking about the weird coordinate systems. One of the weird coordinate system which was gotten by complex variable inverse sine is the hyperbolic elliptic ellipses and then hyperbolas that come in, and they are all very nicely orthogonal. So there, you imagine a hyperbola coming through here, going around the thing. That would be a coordinate system that was orthogonal, and the basic idea is that one of them depends on the difference. This one depends on the sum. If you're making an ellipse, you draw it by making the sum of these radii a constant. So you can reproduce that by just tacking a string here, and then running the pencil so the string is always taut. But when I wrote this paper, I wanted to make a calculator that would make the difference between these two the same. That meant you had to have a little pulley underneath the thing to reel out the string, giving each one equal amounts as you reel. So that would give me a hyperbola around this focus. You follow me on that? So you can either make the sum constant and you go this way, or you can make the difference constant and you go perpendicular to this one. That's the main point. Okay, so that's a piece of geometry that's in what we're going to be doing here shortly. So no matter where you are on that thing, you're going to have two momentum circles that have Thales rectangle in them that define this business about P dot x and its relationship to the eccentricity vectors. Works for hyperbola as well. Okay, well, this is the next few pages show this construction. This is all you need to do to construct a general Coulombic orbit with ruler and compass. I mean ruler because sometimes you want to measure, but you can actually do it with rule and compass. So this is a ancient geometry technique that we're doing here. The idea is that you pick a launch point. Okay, you got this force thing. You blast off point, picked right there. Okay. And then you specify an elevation angle, and I like to use this angle, and you see why that is, I hope, by the end of this lecture. The angle that this thing makes with the radius. Okay, so gamma equals 0 means you're falling straight down. If you're thinking a quantum mechanical atomic orbital, you're in an S orbital if you're doing that. Okay, everything else has got some angular momentum, and it can be a P, D, F. It means angular momentum 1, 2, 3, and so forth. But in this case, I just pick a direction. Okay, and I don't even yet specify how fast I want to go. I just pick a direction, and that's going to be have an orbit on it, have something that goes. Now the speed, the kinetic energy is going to be the important part of figuring out what orbit you get that starts with that momentum. And maybe if it has really a lot of momentum, it'll just go along that straight line. The heck with this thing, whether it was attractive or repulsive, doesn't make any difference. But most of them, if it's attractive, are going to bend down and do something like that, or like that. That's what we're going to be calculating. Okay? So the next step after this, and let's get all of these synced here so that we can talk about the details without squinting eyes too much. There's 3 steps that you need to do. 4 is pretty much the end of getting the focus locus. That's what you're after, and then you want to know where that focus is going to be for certain situations. So that's just setting the stage, and then all you have to do is copy the gamma angle to get another line. That, remember, we had a focus locus for the Rutherford scattering, was just a vertical line. This one will depend on all of the settings that you made here for the launch angle and whatever latitude you want to launch from. And this particular thing is the focus locus because you just imagine what happens. The line R from the first focus, that's this one, okay, will reflect off of this. That is, this guy right here reflecting off of that should point. Basically, what I guess I'm saying is this guy and this guy. Back off so I can see the whole picture here. The line R from the first focus, that's this one, reflects off the line P. That's this guy right here. Okay. Bounces, bong, right? Because this angle is equal to that. That's angle of incidence, angle of reflection. They're both scalable. Okay, so that's what I did when I copied this angle. I made a focus locus just by copying it right there and then drawing it all the way through. Okay, so somewhere on that line, depending on what else we say about this orbit, whether it's attractive or repulsive, how fast it is if it's attractive, we will be locating a focus somewhere, and then we'll draw the orbit given those 2 foci. That's the idea here. Okay. So, the next step is to copy the double angle, this thing. So we just copy it down here. Copy it right down here. Now basically what this is doing is making a line that is perpendicular to the momentum. So if you have another way to do that, fine, but that's probably the easiest way to do this in a general case, if you're playing with this as a geometrical exercise. So there's the focus locus, and there's this thing. And that turns out to be a kinetic energy ratio scale. That's it took me a while to discover this, but the basic idea is that you then mark it off in whatever scale you want to do. If you have a scalar already, you just draw parallel lines to make, say, 10 little tick marks. Here I'm doing it in quarter, half, 3/4, and 1, but these are all minus right here. In fact, all of them, all of the orbits that are attractive have R values. That's the ratio of kinetic energy to potential energy that is negative. And then all of the repulsive orbits, the Rutherford-like things, they're all somewhere on this side of the scale with positive values for this magic ratio. So we're used to sums of KE and PE, actually sum and difference, depending on if it's Hamiltonian or Lagrangian, but here we use a ratio. This is not standard. This is weird. Okay, so so I say the next step is to tick it off so that you have actual marks here. Now this is the deal. The deal is that we are talking about a ratio of kinetic energy to potential energy, which is that thing. How did that come about? And I say, to be proved later, but have no fear. I'll do it in the center screen here, just to get it, and it'll be testing our link. This will take me ahead about 4 or 5 pages to the derivation. The derivation of that particular ratio is right here. There's the eccentricity vector. There's it written out as momentum times angular momentum. And angular momentum is an MVR, but it's multiplied by a sine of gamma. The gamma determines the lever, how close to directly in RU. And then the Km, of course, goes there. And this is being multiplied by a unit vector in the P cross L direction. That is perpendicular to both P and L. L's out of the screen, so this thing is perpendicular to P. And remember, that's what we set that thing up with. So when you write all of that together, you get an MV squared over 2 times 2. There's no 2's there, but I put them in. And then the RO comes down to be a Coulomb potential at the bottom here. So there's your potential energy, there's your kinetic energy. That's the ratio that we're dealing with, and it's being multiplied by sine of gamma, 2 times the sine of gamma. So end of proof, okay? So let's go back real quickly here to page 67, which is where we started, and finish the construction, both that one and this one. Now one of these gets finished with a hyperbola, that's this one. This one gets finished with an ellipse, because this ellipse has a nice negative point here with the ratio less than minus 1. Okay, starting out here at 0, minus a quarter, minus a half, minus 3/4. Minus 1 is where this thing goes to. There's one point there, I should say, we imagine there's one point there which makes a parabola. But in any case, all of the points here cause an orbit that comes back. As soon as you get to that point, exactly to that point, you make that set of measures 0 called the parabola that has an eccentricity 1, exactly. And then anything down here with more, I should say less than minus 1, minus 2, minus 3, minus 4, all the way to infinity, those are all of the other hyperbolic orbits that have escaped the neighborhood of this particular force center. Okay? This particular force center. That's a nothing burger focus, right? Okay, so that's the basic idea. Now, over here, what I did was I went for the positive axis of this this R scale, this ratio scale. All of these are positive. So every one of these is a hyperbola. A hyperbola that is repelled by the force center. Okay, so those are the things. Now all of this is available on the, there's a hyperbola that's the same as this one, and there's a derivation. I'll just go through and extend the derivation with a particular example. Okay, and this particular one is a hyperbolic one. It is pointing to ratio of +1/2. And that goes to infinity. Now this is the actual construction that this thing does. Now what I should do here, there's a movie here, an embedded movie that shows how you play with this thing. Okay, you just go in there and set your initial conditions, and the epsilon vector will be made according to where you drag it. Okay, and then when you release it, you get an orbit for that particular eccentricity vector right there. And this is something TC built, and I didn't have at all anything like that with old-fashioned animations that we have worked with so long. So the next thing we're going to do is something else that TC has really helped with, and I want to show that in just a minute here, but I think I'll go ahead and maybe just using this one and hoping the things go ahead and work the way they're supposed to. I'll do the Lynch Detector, in real time here, I hope. Yes, so there it is. And you see what TC has also added is the momentum vector. And that's what we have to talk about next. That's why it does that, and show some better examples of the actual graphics that goes with that. So whenever you have something like this, you can just go in there and play with it, set your other focus. Takes a little bit of practice, and often you find yourself with your P vector off the scale, or in some part of the thing that doesn't make something you want. When you release it, it will usually make something that returns. In this case, I'm staying with the less than -1, and you resume when it stops to finish the orbit, if it can be finished. So that's what we're dealing with here. And obviously you very often want to erase the paths if you want to start over, or pause and erase the paths, and just pick any old point out here, and build. There's obviously going to be an ellipse that orbits around those 2 points, and I can bring this epsilon down to be very close, getting close here to the -1 case, but not quite there yet. It seems to be hanging on r equals 0. There we go. There's the epsilon right there. R of course will hang on there, but here I go to about 1/2. That's a pretty symmetric orbit. This is a pretty big orbit, and you can have them go, way far away. You wait 5 minutes, and it comes back because we're within this region with our epsilon. This is the epsilon pointing to the actual R value, and that's the eccentricity for this particular orbit. Okay. All right. Let's pause all of this and go ahead with a little bit more algebra. Okay. Now this isn't the most elegant way. I'm pretty sure there will be better examples of this. And there's the movie that tells you what the how to sort of jerk these things around a little bit. So you can see you were running this yourself, probably not quite used to how to make it. It is a little tricky to
Still
run.
not.
But
It's non-intuitive.
yeah. Okay. Let me go ahead here. Now I want to see what momentum does. I know what R does, and I got to get an equation for the polar angle in order to know what the momentum does. And so we're going to be working with phi dot and R dot using the equation of the ellipse, and that's the square of our usual radial equation right there. And then here's the derivative of it, and this is the thing that's constant. Phi dot obviously is L over the inertia mr squared, rotational inertia, And so you get an equation that looks like that can be matched to some things. The r dot that we have here works out fairly nicely. So we want to make use of some of those things using the square of our actual orbital equation. So we end up with a thing that looks like this. And we'll be getting something that gives us an x and a y coordinate equation. Here, of course, using the polar angle definition of it. But here's what the x dot and the y dot do. That is, if you're tracking y dot, it's going to have a fairly complicated looking collection of sines and cosines, but they cancel really beautifully. Just cancels down to that. Let me go ahead and get all this up on this screen with the answer and the actual statement of the result. That is really quite remarkable, I think. This is certainly one of the more beautiful things in the Coulomb orbit world. It should be taken, made evident, shown in this. And that is that the, that the P traces a circle. There's the mk over L sine, there's the mk L over cosa, but an extra distance here, the eccentricity, whatever that is, and if it's not 0, it's got an off-center circle. Okay, so there's the algebra telling you that, but now let's just spend some time looking at that. Now, before I had TC's program completely working, I laboriously went through this, and I'll go through this very quickly on the center screen here. Just went through and did a geometrical construction of the momentum circle based on just the circle of the orbital. We imagine this is where everything gets launched, and we're studying the various elliptical orbits, starting with this one, and there's that Fayetteville's rectangle construction of the p vector in scale. It's starting to pick up speed now. P's getting bigger when it reaches the top, our top, of the orbit. Okay, you see it has gotten many times longer than what it was started with, and here it is getting bigger and bigger and bigger. Okay, and there's just a few steps here that do that, but it's, this is not something, this is a hobby. I shouldn't be making a big fuss about this, but it is, really very beautiful. Now, it's probably time just to go ahead and show, and I'll get it on here in static form. It's already down. That's the end of the story right there. But here I have an animation link that I can make use of. Let me get it going here. And you see the little green thing there? That little green thing made that arc, that circle. Okay? So this really shows that structure of the momentum, making a circle. And it's a big leap there as it goes by the perigee. When it's at the apogee, the p is really small, and then it gets really huge because the perihelion is pretty small, and it's the proportional inverse of that. So I thought this is something that you can really play with. In fact, I'd like to thank TC. If you could give him a hand for building what is really a remarkable piece of geometry that has quantum mechanical significance as well. That's to be explored later on. Okay, so that is pretty much all I want to say about this kind of geometry. And I could, of course, go up here and see if I can make a really ridiculous one. I'm going to try to get the eccentricity vector to. Now, one of the things that is hard about this is getting the eccentricity vector on the other side than the one that you started on. You remember the trick to do that.
I
My
usually have to
eccentricity is
stop
kinda-
and restart a few times and then I get it
Yeah.
back in alignment.
I'll just do one that's getting real close to R minus 1. That's pretty daring right there. See the R equal minus 1? And I'll pull off a little bit here and see if I can get it to... Whoa.
I believe you just snapped a picture.
I snapped a picture. That's very good. Yes, I didn't want
I'll
that
search the
picture
features.
particularly well. Let's go back out of there and keep going here. I want to see that eccentricity vector. There we go. That's what I'm after. It's an eccentricity vector that's, you know, approaching minus 1. But let's not go too far. We'll be here all day waiting for it to come back. That one probably ought to behave pretty well.
It's still a little shallow.
Now it's on it. See, it's making a pretty big ellipse here, right? If I'd gone any further than this, we're already going to be here longer than I really want to be. It's going to come up here, cross the eccentricity axis. That's the axis of the conic section, which is an ellipse, pretty big ellipse. So it's really going slowly now. And the little green circle, you see the little green dot there making the circle. Now it's starting to fall again. Now we're falling, picking up a momentum. And also changing direction so that that little green dot stays on the circle. And we're just about where we started. There we come. Fall, 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 fall. To the
Completely.
perigee. Bingo. Okay? So that's, you know, that's the kind of thing that this lets you do really easily. Okay, here's the parameter system that works best, I think, for orbits, and I would use this. I was an astrophysicist because it shows it shows you a lot of things, and also it's a nice way to do perturbation theory of orbits, where you have other fields working on things. By the way, the R scale here is also drawn in this sequence, and that is done automatically with TC's programs. Okay, this business here is kind of neat. The R, KE over PE, and the ratio B squared over A squared are parameters that we've already talked about, but the fact that you can write them very easily in terms of R and gamma and get much simpler algebra, I think is worth noting. And that's kind of a summation of the whole idea right there. Okay, now normally I would stop the lecture at this point, but we've got a few. I think if I'm going to take a couple of minutes just to show you real quickly what it is we will leave as a study lecture. This is lecture 27 that I'm going to leave as a study lecture. And this is out of the textbook right here. This is an explosion right here that in the old program that I had back in the Stone Ages. Let me get this one ahead as well to this point. These are excerpts of the paper that came out describing a lot of this. But the basic idea here is, once again, a contact point, okay, occurs where you use from the center here, where you have the both foci employed, but one of the foci is actually here for the envelope. So the long distance to a focal point of the blue envelope has to be in line with the point that's contacting and the focus of the little orbit here, Okay, so I have two ellipses that are being married, so to speak. One of them using these two foci, and that's the orbit itself, and then another pair that's this one and this one, building the thing that surrounds it and contacts it. In this case, only once, right there. So that's the thing to look for in these animations that I'm going to try to show that go with this. Perhaps the most spectacular one is this, and I hope that this machine is fast enough to get us through it, but I'm going to blow up a bomb right here in the Coulomb attraction center is here. It's attraction this time. So, boom, okay, and roughly, let's see, it says here, number 200, that's perhaps a little much, but makes a continuous drawing. At first it's a circle expanding, but then this is attractive, so these guys are showing that that's attractive. And now the computer has to slow down to calculate a lot of stuff because we're getting close, and it's in order to maintain accuracy, it has to slow down. It does a little loop-de-loop, so now we got a bunch of the fragments coming or orbiting around that thing and coming back out in what looks pretty much like a circle, but an off-center one. And so all of these points here are going to pass the ones that are on the slow path to getting to the center of this orbit. Now, I've never seen that this happens anywhere. I mean, this is just really remarkable. This is one of those things you can do with geometry too, but I won't bore you with that. We're about halfway now. When these guys pass each other, and I'm going to do it just a couple more steps here. And while we're at it, we're drawing it with color for Lagrangian so that you could make a wave function out of this if you adjusted it properly. But this is pretty close to one. You can see that the coloring gradation maintains shape, so you're close to a quantum state. So now the loop-de-loop is going to close. Now finally these slow guys get to visit the fourth center. And remember, it blew up here, okay? So if you're out in space and you have a bunch of junk you want to blow up, and you blow it up, don't think it's gone. It's going to be back. All with a vengeance. And so here, this thing finishes the loop here. Now it's on the upside of recovery. And here has to slow down because there's so many points that have to be tabulated, so step slices now. And it was bang, and now it's whatever bang is backwards. It's crunch. They all return to the point that they left. Just like that happened with a couple of examples that we showed with a harmonic oscillator. Okay, I think that's pretty much all I want to show. The other thing is solar wind and a comet. If it's an ideal situation, a solar wind and no other funny stuff going on, a comet head is a hyperbola. That's kind of neat. Okay, and you can imagine astrophysical situations where the comet had more energy, on the average, to surround the repulsive. In this case, it's a repulsive place. And if you pick it just right, you can make the comet have a flat head. So it can be anything from what we saw before to this, to something that goes around. And you're making hyperbolas as envelopes now. Hyperbolic envelopes of hyperbolas are being made here in this particular case. Okay. Well, I think that's about it. That's the paper that goes with this thing. I hope you enjoyed this, and I hope you have a good Thanksgiving. This will interrupt your enjoyment of it with nightmares of being crushed by the exploding space bomb. Okay. And if you got the email, the problems are due after Thanksgiving on Monday, so.